Okay, hello everyone. So I think we should be live now, and hopefully you are also able to hear me and see me. Perfect. I think that you are able to. So let me welcome you to this workshop, and the topic of this workshop will be quantum programming and the Microsoft Quantum Development Kit. So I would like to tell you about a couple of organizational things before we start. So this workshop will be held in English, and the main reason for this is because a lot of the topics and the concepts that I will be talking about is familiar to me rather in English than in Slovak. So even if I would be having this workshop in Slovak, it will be half English and half Slovak. So for this reason, I decided to have it simply in English. So this is one thing. And regarding the workshop, there will be let's say short. I think it will be a 30 or 40 minute theoretical part, because it doesn't really make sense to start quantum programming without knowing about the concepts and why we are doing this actually and what we are trying to achieve. So I will have a presentation for you that will describe the concepts, and then we will switch to some live coding and some workshop where I will be showing to you how to actually write a program that will be running on a quantum computer. So this will be it. And if you will have any questions, feel free to ask me either in English or in Slovak on Slido, and I will be happy to answer. I will be following up on the questions, and I will be happy to answer if I will be able to. So I think that's it from my side, and also a short introduction, and then we can start. So my name is Tibor Csiba, and I am working for Accenture. So I've been with Accenture for almost 10 years now, since graduating on the Faculty of Electrotechnics and Information Technology. And this is actually my first company where I'm working. So yeah, it's been 10 years now, and along these 10 years, I've been mainly working with Microsoft technologies. So I was working with Microsoft and the .NET framework and building software on this platform. I think this is enough for the introduction, so let's get to some more interesting topics, hopefully. So let me start with the agenda. So what will we have on the theoretical part today? I will start with some discussion about the purpose, the history, and the current state of quantum computing and where we are aiming with this whole topic. Then I will give you a short introduction to the quantum world, because there are some concepts we need to be familiar with before we start actually writing some software for quantum computers. Then I will show you some quantum computing basics, and I will compare it to classical computing so that you can understand better what is the main difference and what are the advantages of quantum computing over classical computing. And then we will also discuss where is this useful, or what is the purpose of building quantum computing software. What are the applications that we are actually where we are actually able to leverage quantum programs, and what is the edge this gives us. And then finally, after all this theory and discussion about the purpose of quantum programming and quantum computing, we will be having a look at some practical examples. So we will be looking at the Microsoft Quantum Development Kit, and I will tell you more about this. So Microsoft developed a programming language which is suitable for programming quantum computers. And I will show you how to leverage this platform, how to write your own quantum software, and how to run it currently on simulators and later on real quantum computers. So that's the plan, and let's get to it. So let's start with some introduction of the big picture, of the big topic. What are quantum computers? What is the purpose? So there are a couple of applications today, or issues today, or let's say problems today, which we are trying to solve with classical computing, but this is impossible to do so, because it would just be an impractical amount of time required to solve these problems. I will talk about these problems in more detail later on. But just as of now to know, the important thing is that we are not able to solve a couple of issues with classical computing, which we should be able to solve with quantum computing. So these are in the areas of, let's say, environment, health, energy, material science, and others, which we potentially haven't encountered yet. On these pictures, I just wanted to depict you that the quantum computers are very different from the classical computers, so they look totally different. For instance, on the left side, on the left picture, you can see IBM's quantum computer, and on the middle down picture, you can see Google's quantum computer. So this was the quantum computer they were using to actually achieve quantum supremacy. I will talk about this a bit later as well. So this is why we are trying to build quantum computers. Now, I would like to just go through the short history of this whole concept, and I will not go into the details, and I don't want to bore you with the history of this stuff. But what I just wanted to show you by this is that the whole quantum computing is built on the principle of quantum mechanics. So this is a very important physical theory. And usually it's said that quantum mechanics and Einstein's relativity are two of the most important concepts of physics and the most important theories of physics. So you probably heard about one or the other. You surely heard about Einstein's relativity. So quantum mechanics has the same importance. And nowadays the biggest challenge is to try to actually unify or unite these two theories into grand unified theories. So the point is that this theory is old. So this is really old. This theory is started around 1900. So it's more than 100 years old theory. It's nothing new. It's been around for a while now. What's new is that we are able to leverage this theory currently. Actually, we are trying to, and started to do so, to build quantum computers. So when this whole concept of building quantum computers on quantum mechanics started? So it started in 1981 by Richard Feynman, who stated that some of the systems and some of the problems we are dealing with, we are unable to simulate on classical computers. So this was the first point in history where quantum computing and the need for quantum computing really came into existence. Later on, there were some algorithms which were found, for instance, in 1994 by Peter Shor, who theorized that quantum computers could be used for factorials and factoring integers. And why this is important is because in cryptography, factorials play an important role of securing, of making sure that the encryption is not breakable. So this would potentially mean that quantum computers could break the standard cryptographic algorithms and break the encryptions we are currently using. Then in 1998, there was a first quantum computer. This was a 2-qubit computer, but it was, let's say, working just for a couple of nanoseconds. So this was more like a very, very basic first prototype. And in 2017, Microsoft introduced Q#. So this is the quantum programming language we will be using today. And after this point, Google was also announcing that they were using a quantum computer to achieve quantum supremacy. So you probably heard this in the news. And what this means is that they were using their quantum computer for a very specific algorithm to solve an issue that would take a classical computer thousands or millions of years. I'm not sure about this. But this is highly controversial because this was just a very specific algorithm, and I think that this is not even usable in, let's say, normal life or for solving practical problems. So this was like, you can imagine this as the first flight that the Wright brothers took. So it wasn't useful for anything. They just showed that it can be done. So this is all Google achieved currently and nothing more. In 2019, IBM actually introduced an online platform that gives you an access to their quantum computer. So what you can do is that you can go to their site, and via the cloud you can program their quantum computer, and it will be running, your program will be running on a real quantum computer they have somewhere in their laboratory. So, in actuality, in 2020, a famous quantum computer manufacturing company, D-Wave Systems, they gave free access to their cloud platform for researching against COVID-19 and finding a cure for COVID-19. So as you can see currently, as we have the COVID-19 pandemic going on, this would be really important to have quantum computing already ready, because we could potentially find some cures and find some vaccines much more quicker with the help of quantum computers. So I think this is it regarding the short history, and I would also quickly touch on the topic of where we currently are with this whole thing of quantum computing. So you can imagine these quantum computers as some huge machines somewhere in laboratories. There are a lot of issues currently with producing this for mass consumption. So you probably shouldn't expect quantum computers having in your mobile phones for tens of years from now, because there are a lot of issues with this. And we will go into more details why this is currently impossible. As we mentioned, the theory is really old, and what we were really struggling with, and we are currently struggling with as well, is the engineering. Because we know how to build them, but we need the tools, we need the technology to be able to build them. And this is currently an ongoing process. There is a lot of research being done by huge companies to try to actually build the hardware that would be the quantum computer, because this is not a trivial task. And then there are other issues. So with these hardware issues, this comes the problem that this hardware really needs to be isolated. There are a lot of issues like vibrations, the temperature fluctuations, electromagnetic radiation, and so on, which make it impossible to create these quantum computers for mass production and mass consumption at the moment. So the current state is that this is a very complicated device. It needs to be held in isolation. There are some huge companies like Google, IBM, and so on, who have these quantum computers in their research labs. And the future will probably be that you will be able to leverage these quantum computers via cloud access. So as currently we are moving to the cloud, and everything is moving to the cloud as a service model nowadays. For instance, streaming, gaming, huge workloads, companies are moving to the cloud with their software solutions. This is probably the way how quantum computing will work. So you write the quantum software, you create a quantum program, and then you will leverage the cloud of a quantum provider or a quantum computer provider to run this program. So this is probably how this will work. On this slide, you can also see a prototype. So this is called the Tangle Lake 49-qubit quantum processor. And this is currently something Intel is working on. So this resembles a CPU, which is in mass production today, but it looks a bit different. This is currently in just prototyping phase and not a real device, definitely not for use in any application nowadays. So I think this is all I wanted to talk about regarding the history, the theory, so quantum mechanics, and the current state of the quantum computers. And now we can delve deeper, and we can start describing the quantum world and the quantum concepts that are important for us to be able to write the quantum programs. So we can start with probably, I think you already know this, the Schrödinger's cat thought experiment, which demonstrates a very important functioning of the quantum world. So this is superposition. This will be very important for us because this is something we can leverage in our quantum programs. So what is this thought experiment about? Probably you heard about this, but I will recapitulate for you. Basically, we put a cat in a box, and then we put a system in a box that has some poison, and this poison has a 50% chance of being released to the cat and 50% chance of not being released to the cat. So this is like a quantum system because this is based in the decay of the molecule that will trigger this poisoning, and there is a 50% chance that the poison will kill the cat and the 50% chance that it won't kill the cat. So if we are not looking into the box, we can say that the cat is 50% dead and 50% alive. Of course, we know that this is ridiculous because this is not how, let's say, the real world works or our world works, but this demonstrates how things work on the quantum level. So on the very tiny molecular or particle level, this is what's happening actually. So until we are measuring or we are looking into the box to see whether the cat is alive or dead, the cat is in a superposition of being both alive and dead. So we need to make a measurement to collapse the superposition, to cause decoherence, and to collapse the wave function, let's say, of the cat, to make sure that it collapses into either being dead or alive. So this is a very interesting thought experiment Schrödinger was proposing to demonstrate how things work on the quantum level. And we will be using this superposition a lot when we will be writing our quantum software. So this is one principle we need to be aware of. Another important principle of the quantum world is quantum entanglement. So this is something what Einstein called spooky action at a distance, because this principle or this reality actually violates relativity. So you probably are aware that information in our universe cannot be propagated faster than the speed of causality or the speed of light. So you cannot transfer information faster. The problem with this principle is that in quantum mechanics, this is not the case. So it is possible to entangle two particles, two quantum mechanical objects in quantum mechanics, and once they become entangled, they kind of form a single system. So what this will mean? This will mean that if we observe the state of one particle, we actually automatically know what the state of the other particle will be. So immediately we have the exact information about the other particle, and the other particle also goes into the same state as, let's say, the first particle which we measured or observed. And this happens instantaneously. So this is not propagated with the speed of light. This happens immediately. There were a lot of experiments to demonstrate this. What's really interesting about this is that this is not working for a small distance. This is working on theoretically an infinite distance. So I think this was an experiment done by the Chinese. They were able to demonstrate this entanglement by putting two particles on the two opposite sides of the world, or almost, it was, I think, 1,000 and something kilometers. And they were able to entangle these particles. So they kept this entangled state, and they were separated by a distance of thousands of kilometers. So this is a really interesting thing that's happening on the quantum level. And this is also something we can leverage in our quantum programs. So we have superposition, we have quantum entanglement, and the last and but not least concept which we need to start writing some software for quantum computers is the measurement itself. So we already discussed that there can be everything in the quantum world until we don't actually measure it is in a kind of a superposition. Particles can be entangled and so on. what happens is that measurement collapses this state. So it collapses the superposition and it puts the particle in a very definite state that we are able to observe and we are able to measure. And the very famous experience or experiment for this measurement is the double slit experiment, which is probably the most famous experiment in all of physics. This is not really a core concept. What we need to know is that when we measure a particle, it collapses into one state or the other. But I thought that I will also shortly describe it to you, because this also demonstrates very well how measurement collapses this fuzzy state of a particle being in a superposition. So what's happening here is that we have a gun that's firing electrons, and we have two slits. And we are following where are those electrons actually fired on a screen behind these slits. So what is it that you would expect? You would expect that the electron goes through one slit, or it goes through another slit, and then you would see on the screen a pattern of these two slits. But what's happening is that this is not the case. So what you see is an interference pattern. And the only way this can be described why you are seeing the interference pattern is because the electron doesn't go through one slit or the other slit. It actually goes through both slits because it propagates as a wave. So it's kind of in a probabilistic superposition, and it doesn't have a defined position. It just has a probability of going through one slit or the other slit. So what's happening because of this superpositional state is that it propagates through the slits as with a probability of, let's say, 50% going through one, 50% going through the other, and it goes through both slits as a wave. So that's why you are seeing the interference pattern, because single electron is propagated as a wave. So this also demonstrates a very weird concept, is that until we measure a particle, it doesn't have a definite state. It can be anywhere, more or less. But once we start measuring, so say we put a measuring device before those slits, and we measure where is the electron going through, there will be no interference pattern. So what will happen is that the electron will go through either one slit or the other slit. So again, measurement collapses this wave-like behavior of the electron, and the electron resolves its position of going through one slit or the other. So what this concept is telling us, and what the purpose of this demonstration of these quantum mechanical principles were, is that we can leverage this superposition, we can leverage this quantum entanglement, and we can leverage this fuzziness to encode more information to the quantum system, as if we were working with classical computing. So this is the main purpose of doing this. And now we are slowly getting to the quantum computing basics, and we will do some comparison with classical computing. So we should now have the theoretical knowledge of knowing how the quantum world is working, and now we will be able to understand why quantum computers give us an edge in some specific applications. So let me have a very, very short break and see whether we have some questions. So far I don't see anything, so just give me some seconds. And we can continue. So, when it comes to quantum computing, this is exactly how we are using these principles. So, we were mentioning the word quantum a lot of times, but we haven't really clarified what the word quantum means. So, quantum is the smallest amount of unit of something, in this case, let's say energy. For example, as we were talking about the double slit experiment, we were sending these photons in quantums. So it means that one photon represents a single quantum and it cannot represent a smaller energy state. So you cannot divide the photon into smaller parts. A quantum is just a very basic small amount of energy. And how we are using this. So let's talk a bit about how classical computing is working. How classical computers work is that they use bits. So those bits can be either 0 or 1. Probably know that all our computers, every hardware we have currently is working on this principle. So you have the hardware, inside you have the CPU, the processor, and the processor contains some small, very tiny microscopic switches, which are called transistors. So these transistors are switching the signals from 0 or 1. This is realized by electricity. The transistor is either switched on. If it's switched on, it represents a 1. If it's switched off, it represents a 0. And with this, with putting billions of transistors on our current chips, we are able to do some very sophisticated logic of computing. This is how we are working with our computers nowadays. Now, what is the biggest difference between classical computing and quantum computing? So the difference is that in quantum computing, we are using quantum bits or qubits. And this is where the concept of superposition starts to be very interesting. Because if you have a bit in a classical computer, this can be either in a state of 0 or 1. There is no intermediate state. The transistor is either switched on or switched off. If you have a qubit, you are able to put the qubit into superposition. And what this gives us is that the qubit is not in a state of being 0 or 1, but it's in a state of being 0 and 1 at the same time. So this can be demonstrated also by, as you can see on the right image, a Bloch sphere. This is more like a geometric representation of this, but I don't really want to go into the details of linear algebra because that would be too complicated, and myself, I really just understand the concepts and I'm not good at mathematics. So I just want to show you the concept. A qubit can hold the information of both being 0 and 1 at the same time. Now, what can we use as qubits? So we can use photons, we can use some atomic nuclei, we can use electrons, we can use any quantum system, let's say, which we can put in the superposition of being 0 and 1. And you can ask, but what is 0 and 1? So if we have an electron or a photon, what represents 0 or 1? So what we are currently using is the spin of this particle. So the spin is a property of quantum mechanical objects like electrons, atomic nuclei, and so on, which you can imagine that it can point, for instance, upwards and downwards. So by using the spin and the polarization of the spin, we can represent 0 and 1. But the point is, until we measure the spin of this particle, we cannot determine whether this is 0 or 1. It is both 0 and both 1 at the same time. So this is, again, why superposition is important. But how we are using this in our quantum programs? So as you can see on the images, you can imagine, or let's say that you have 2 bits on a classical computer. What kind of values you can have on 2 bits? So you can have 4 possible values there. So you can have 0, 0, 0, 1, 1, 0, and 1, 1. And that's it. You cannot have any other different values. And you, at one moment in time, represent this information with 2 bits. So what I can ask you is that please give me the first bit and please give me the second bit. You have 4 possible values and that's it. If you have 3 bits, you have 8 possible values and so on and so on. So for instance, with 2 bits, you can represent 4 numbers from 0 to 3. With 3 bits, you can represent 8 numbers from 0 to 7. And this is where the difference comes into place. So with quantum computers, you have the quantum bits, and with 2 qubits or 2 quantum bits, you can have 4 values, but simultaneously. So you don't have either 0, 0, 0, 1, 1, 0, or 1, 1. You have all these values, let's say, at the same time. So while in a classical system, you have 2 bits of information with 2 bits, in a quantum system, you have 4 bits of information with 2 qubits. And again, it's the same for 3 bits. In a classical computer, you have 3 bits of information coded into the system, but with a quantum system, you have 8 bits of information. So the information density, because of these superpositions and entangled states in a quantum computer and a quantum system, is much, much higher. So the mathematical relation of the information we can code in a quantum system is 2 to the power of the n, which in case of 2 bits is 2 to the power of 2, and in case of 3 bits, it's 2 to the power of 3. So now we can start to understand how much potential quantum computing has. Imagine that we are able to build a quantum computer with 300 qubits. So what we could do with 300 qubits is to, if we would put these 300 qubits into a fully superpositional entangled quantum state, the information we can store with these 300 qubits is 2 to the power of 300. And this is interesting because the total number of atoms in the universe, so all the matter the universe contains, is around 2 to the power of 300. So you can imagine the enormous amount of simulation and computational power we could achieve by building a quantum computer this powerful with 300 qubits in a fully superpositional entangled state, which is currently, of course, not possible, but it has a really, really huge potential, as you can see. So the main points to take away from this theory is that quantum bits differ from regular bits because they can hold zeros and ones at the same time, thus containing much, much more information. Okay. And now, slowly but surely, we are getting to the end of our theory. So I would also touch a bit the concept of measurement and why and how we are able to design these quantum computers and what are the challenges. So, as mentioned, to leverage this computational power, this inner state of the system needs to be in superposition and entanglement of qubits, and it needs to be very carefully designed. Any kind of problem, so this is where we have these quantum computers only in research labs. Some temperature fluctuations. So for instance, to be able to differentiate between the spins pointing up or down, so to know whether the qubit is in a state of 1 or 0, this is a very small difference in energy density. You need to have very low temperatures. So currently we need to maintain temperatures just a few degrees above absolute 0, which is very challenging. No vibrations can occur, no electromagnetic radiation. So if you put your mobile phone near a quantum computer, it will be in a decoherent state, so it will not work. So they are very delicate devices, and it is very tricky to actually have these quantum computers working as they are intended. But we were talking about measurement as well. So we are not able to measure the inner quantum state of these quantum computers. The only thing we can do is to design this state of qubits in a specific configuration, run our quantum algorithm, and put the system into a state whereby measuring the final state, when we collapse the whole superposition and we have a definitive result, we are able to make sense of that result so that we can measure what we actually achieved. So this is the very tricky part, and it's definitely not a trivial thing to do. So apart from very tricky part of engineering these systems and building these quantum computers, the algorithm part is very complicated as well, and then the measurement is also a complicated thing, so you need to know how you measure and what you measure. So the thing is that you might be wondering whether quantum computers will ever make our regular computers obsolete. Currently, it looks like that this is not the case, because currently we know just a few algorithms where quantum computers give us an edge over classical computers. So probably they will not be a replacement for current computers. It looks like that they will be something that will be added on top, or they will be helping current computers in some specific algorithms and calculations. So there will be some algorithms where we will be applying quantum computers, and the other workloads and other algorithms we have now, we will be just using our classical computers. So they will probably exist in parallel in the future. And the thing is that they are usually not even faster. So quantum computers do not give us superior computing performance when it comes to the speed of computing. The point is, as we will see, I will briefly touch a couple of algorithms. The point is that they can arrive to a solution much faster. So you don't need to do that amount of steps to arrive at a solution that you would need to do if you were using classical computing. So by doing much fewer steps, you can arrive to a solution much faster. And currently, there is also a big debate of, and you can hear in the news that one company was building a quantum computer with that many qubits, the other one was building computer with that many qubits. These qubits really differ in count and in how they are working. The thing is that based on the technology, for instance, if you have a 50 qubit quantum computer and a 150 qubit quantum computer based on different technology, they can have the same performance. So do not think numbers. The number of qubits doesn't mean anything. And especially when it comes to the computational power, the number of qubits doesn't mean anything if you cannot have the correct state of superposition and entanglement ensured within that system. So here you can see on this picture, if you are adding more qubits, but you have a high error rate, so decoherence happens, you have some temperature fluctuations and so on, you will not achieve higher computational power. So this state really needs to be maintained and without any issues or any effect of the surrounding environment, and this is really hard to achieve. So I have the last slide for you when it comes to theory, and then we can jump to the workshop part, and we can start exploring how to actually program these quantum computers. So what are the applications currently that we plan to use for quantum with quantum computers? You surely heard about artificial intelligence and machine learning. This is a buzzword nowadays. There are some possibilities of extending this with quantum machine learning. I haven't found a lot of materials on this topic yet, but what I found is that this can be leveraged for some drug design and computational chemistry. So when it comes to drug design, this is not like designing drugs, but this is like designing medicine, probably. So where this can help us is that currently we are struggling with coming up with solutions to design different medicine or drugs, because these drugs, these are molecules. So these are very small particles and they behave according to the quantum world. And by using classical computers, we are able to simulate molecular behavior on supercomputers currently. But when it comes to more complicated molecules, so for instance, if we compare the molecule of caffeine found in the coffee, we are able to simulate the behavior on a supercomputer, classical one. But for instance, when it comes to the penicillin molecule, which is much more complex, we just don't have the computational power to simulate this. This is just too complex. And this is where we could apply quantum computing to actually simulate this kind of molecules and design new ones, which would help us to come up with better molecules and use it in medicine. Another thing is where this can be used is, so here you can see on the pictures, one is protein therapeutics and the other one is the black picture with that interesting structure is something that's called protein folding. So this is how proteins fold. And as you can see, this looks pretty complicated. So again, this is almost impossible to simulate with classical computing. So you need a quantum computer to simulate this kind of protein folding algorithms. And another application is biology. So on the right bottom picture, you can see something that's called nitrogen fixation. So why would this be important to use quantum computing for this? Nitrogen fixation is a process that's used to generate ammonia. And ammonia is used in our fertilizers. The problem is that this is a very, very complicated process because this generates a lot of heat, generates a lot of CO2, and I think it's responsible for 2% of the world's CO2 emission, which is bad. The thing is that there are some bacteria which can do this automatically on a biological scale. So there are some bacteria which can generate this process of nitrogen fixation, and they can generate ammonia. The problem is that bacteria are small and they are part of the quantum world, and we are not able to find out how they are doing this. So what would really be good is to simulate how these processes are working on this tiny level, how these bacteria are actually doing this, and then we could come up with a much more efficient process that would not harm our environment that much. So as you can see, this is really important to apply quantum computing on this kind of applications, because this could mean that we could be living in a better world theoretically. And let me show you the last example of this application of quantum computing, and then we will actually be ready to start the practical part of the workshop, and I will be going through some programming. So the last area I would like to talk about is cybersecurity and cryptography. So how we can currently how we could leverage quantum computing is that in cryptography you have some keys. So usually you have, if it's an asymmetric cryptography, you have a private and a public key. So what happens is that you keep the private key, you send the public key, and then someone can encrypt the message using the public key. But this can be decrypted only by using the private key. So this is how asymmetric cryptography is working. Actually, what you can do is that you can use quantum mechanical objects, like for instance photons, to represent these keys. And then by observing these information on the other side, let's say on the recipient side, you would know whether there was someone or there was somebody who was able to eavesdrop and who was able to actually read the information sent in the key. Because if someone reads that information, it will count as a measurement. And if we measure this system, then it will again change its state. So what you can do is that you can verify if someone was measuring these values or not. And if not, you can be sure that, okay, then this key is valid and no one decrypted it, no one can use it for breaking the encryption. So there are some very important and interesting applications of quantum computing. So it definitely has a great future. And I think that is all pretty much what I wanted to show you, let's say, on the theoretical part. So now we should be ready to do some practical programming and see how this is working, how these principles are working with the Microsoft Quantum Development Kit and the Q# language. So let's just have a short 2-minute break, let's say, and I will check whether there are any questions so far. Let's have maybe a bit longer break, like for 5 minutes, and then we can start doing some practical stuff. And we can do some programming in Q#. So in the meantime, I'm checking whether you had any questions so far, but I cannot see any. So either there are no questions or I'm looking at the wrong slide, though. But yeah, feel free to ask anything you are interested in. Probably that's not much to ask about this theoretical part. Maybe you will have more questions regarding the practical part, so let's see. Okay, so I think that we should be okay to start the practical part. So, okay, thank you for bearing with me on the presentation. And now let's switch to the practical applications of quantum computing. So, currently, as I mentioned to you, there's not a lot of companies that are providing quantum hardware, and there's definitely not a lot of companies who provide some means of writing quantum software and quantum programs. So one of the companies is Microsoft, and I found this really interesting. I heard about this quantum development kit on a separate workshop actually, and I found this very interesting to have a look at. So I started going more deep into this topic, and I found that Microsoft already created something that's called the Q# programming language. And with Q# you are already able to write quantum programs. Now, just a quick disclaimer, the problem currently is that you can use Q# to write your quantum programs, but they will not be running on a real quantum computer. Because Microsoft is just preparing to start their cloud service of providing quantum hardware access to the public audience. So currently, what you can do is you can write your quantum software You can run it in a simulator. We will show this. And then once the hardware will be ready, you can run this in the cloud on a real quantum computer, on real quantum hardware. So this is just some marketing of Microsoft. This is the global page of Microsoft Quantum. As you can see, they are already advertising possible registration for the Azure Quantum Developer Workshop. So they are starting to have a huge community of people who are interested in this topic of doing quantum programming. So they will have a workshop. I'm just doing some advertisement for Microsoft here. And if you look at Azure Quantum, and this is also the thing I was mentioning, so Microsoft is planning to have access, to provide access for you to their quantum hardware via Azure. What's very hot news is that if you put Microsoft Azure into Google, it should give you some news. Okay, currently I'm not able to find it, but I think it was just yesterday that Microsoft Azure Quantum. This was just a recent announcement that this is going into preview mode. I'm not seeing this shown by Google now, but it was just yesterday they did a big announcement of this. So they are really moving up with providing this quantum hardware. But what's important for us is that they are providing a means of programming this quantum software, and you can access this via the quantum development kit. So this is what's important for us, and this is what the practical part will be about. So on this page, you can find the Microsoft Quantum documentation and also the documentation for Q#. So Q# is a programming language specifically designed for developing quantum programs. And what we will be doing is we will be writing some simple applications in this Q#. And then we will also discuss some more complicated algorithms and applications. And finally, we will close this workshop by showing you where can you find some more samples and how can you participate in quantum computing or quantum programming events and activities. So, in order to start writing quantum programs, you need Visual Studio Code or Visual Studio. Visual Studio is available on Windows and Mac OS, and Visual Studio Code is available on Windows, Mac OS, and Linux. So I would recommend you to grab Visual Studio Code. This is a free text editor, and all you need to do is download Visual Studio Code. I did some zooming here, so you should be able to see it hopefully, and this will not be too small on the stream. I think that this should be okay. And all you need to do is, if you downloaded Visual Studio Code, the first step is to download the Microsoft Quantum Development Kit. So Visual Studio Code works by these extensions where you just grab an extension and then you will get some IntelliSense support, some coding support, and you are able to create some specific projects for the specific workloads. So if you just type quantum here, you will find the Quantum Development Kit, and then you are able to install it. This is all you need to start writing quantum programs. If you choose to use Visual Studio, you can do this even if you don't have a Microsoft license. You can have the community version of Visual Studio. Then you can grab the Quantum Development Kit as an extension. So you go to extensions, and you can find it online. So you just type quantum, and you install the Microsoft Quantum Development Kit. And that's it basically. And from this point on, you are able to create some projects where you are able to write the quantum software. So this is what we will be doing now. So you can hit Ctrl-Shift-P, or you can just go to the terminal, and then you can find these options. Q#, create new project. And this is what we need to do. So I'm not sure whether you already had the chance to download Visual Studio Code. You have multiple options, so you can do these exercises with me, or you can just listen to it later on, maybe via the recording, because there's really a lot of things to cover. So it would be impossible to do so within this time frame. So this is also why I chose this format, that I will be doing some live coding for you, just to give you an impression how this is working, and then you can later on watch the recording and do this yourselves. So let's create a new Q# project. And hopefully this will work. So let's go with a standalone console application. There are some other options here. You can build quantum libraries, which are some pieces of code that you can then reuse somewhere, or you can even unit test your quantum programs. But let's stick with a standalone console application for now. So let me create this project, and let me call this Quantum1. And I am just creating this project now. So this will take some time, and once the project is successfully created, you get a file that's called a program Q#. Okay? So here you see that this is a very simple quantum program built in Q#, and this is just a hello world. So I would like to also apologize for these error messages that you see here. This is because Microsoft has some compatibility issues with the newest version of .NET Core, but this doesn't cause any problems, and they will fix it. Currently, it's just causing some issues with the text editor that is giving us some errors. But don't worry about this. This is nothing relevant, and it's working as expected. So if I run this, you can go and say .NET run. And this is leveraging the .NET Core from Microsoft to actually create a runtime for this Q# program. So what will happen is that under the hood, there is some C# code that creates a simulator, a quantum simulator, and it runs this quantum program. So if we wait a bit, we should see the result. And here you can see that we get this message, hello quantum world. So here we have an entry point, and this is something that enables us to self-host this application. This will automatically create the scaffolding for us, and this will be run automatically. So this operation also represents some operation, and here we just see a message. So this is nothing interesting for a quantum program. Here we can also see some namespaces that are introduced, where we can from these namespaces we can use some functionality. So let's actually write something more interesting. Okay. So instead of hello Q, let's say that we would like to get back a result. So we are expecting a result, and now we can start working with qubits. So this is how we are allocating a qubit. I will type this first program by hand, and then the other ones I will just say more or less copy paste and show you how they are working. So we allocated a qubit. You remember that this qubit can be 1 and 0 at the same time. And now we can apply the age operation. This is provided by the Q# language to put this qubit into a superposition. So this is called the Hadamard operation, and this puts the qubit into superposition. So after applying this, the qubit is in a not define state of being 0 and 1 at the same time. And now what we can do is we can measure the value of this qubit. So if I now type reset z q, what this does is that this does a measurement of the qubit value. We collapse the superposition, so the measurement will give us either 0 or 1. And once this is done, we also reset the qubit to its original value of being 0. Because if you don't reset the qubit, this will blow up and you will get an exception. So this is our very first basic quantum program. So we just allocated a qubit, put it into superposition, and then measure its value. So let me run this. And if I didn't make any mistakes, because currently I don't have IntelliSense support due to these weird errors I'm getting because of some problems with the compatibility, we should be able to see the result, which should be either 0 or 1. Okay, so probably made a mistake. Okay. Yeah, I'm cheating a bit because I actually have... okay, I understand now. So I need to include some more namespaces, probably, because I'm trying to use some functionality which is not included in these namespaces. If this will not be the case, then I will not spend more time. I'll just copy-paste the program and it will run just fine. But I'm not seeing any other syntactical errors, so hopefully it will work. It's not working. Probably I have some error. So let me make this a bit more simple, and let's just copy this code part here. And this should run just fine. Maybe I was missing some brackets or something different. I'm not sure exactly. So, yes, it's working. Fantastic. So, if I run this multiple times, you see that the output is either a 0 or a 1. If I would be running this enough times, then I would be getting 50% of the times 0 and 50% of the times 1. Okay, so this is our very first quantum program. And now let's write something a bit more complicated and a bit more fun. So let me also copy-paste this program here. And you can see that this has much more code, but this is not complicated at all. So what this is this is a real random number generator. Because the problem with random generators using classical computing is that generating something random is really hard. So usually we have some pseudo-random generators which generate random numbers based on something. Maybe you can take the time, or you can take the, I don't know, how much degrees Celsius there is, or I'm just trying to come up with an example, but how do you simulate something random? As we mentioned, we are able to completely randomize the value of the qubits, whether they will be 0 or 1, and we can leverage this to write a truly random quantum simulator. So how this program is working? And now I see we have some questions on Slido, so I will answer those. But let me finish this part, this demonstration, and then we can have a look at the questions as well. So, what is this doing? The entry point for this program is sample random number, and here we are declaring a number of 50. So we are trying to get back a random number from 0 to 50. Okay, and then we are calling this operation sample random number in range. So we are sending 50 here. We are allocating an array of bits, and then we are resolving the size of the bits required to store this integer. So by sending 50 here, we will see what the bit size needs to be in order to store this value. And then we are iterating through it. So here you can see that the language contains the very classical statements all programming languages have. So you can have a for cycle, for instance, you can declare some variables and so on. And now what we are doing is for each bit, we are saying, do we want a 0 or do we want a 1? And then we are just using the code we've written. So we are either getting back a 1 or a 0 from the qubit. And we are putting these 1s and 0s into the array. So here we are concatenating the 1s and the 0s. We are receiving an array of bits, and then we are converting the array of bits back into the integer value, and this will be our value. So let me run this example. And you will see that we will be receiving a number between 0 and 50. Hopefully. But it should work just fine, I think. At least I hope so. This is just some warning, no worries here. Okay, and we are getting back 13. Okay. If I run it again, now we are getting back 36. Now run it again, and now we are getting back 6. So this is a very trivial example of an algorithm that gives us some real true numbers some real true randomized numbers or integers. So this is one very, very simple use case of quantum programming. And once the quantum hardware will be ready, you write these programs, and then this will run on real quantum hardware and real qubits. So this is just a simulation, as we mentioned before. Okay, so this is an example of another program. And yeah, maybe we can have a look at the questions now. Okay. So yeah, let me answer a couple of questions. Let me finish the practical part. And then after that, if you will have other questions, we can also answer those. So there is one question related to the power consumption, whether there is a big difference. As far as I know, the power consumption should be even less than the current power consumption, because there is one thing that these quantum computers currently need to be held in a specific state, and because of this, creating the environment, cooling, isolation, the very tricky problems with the environment, probably the power consumption is high. But once we are talking about the power consumption of the actual quantum computer itself, so the core, the chip, this will be much, much less than currently, than with our current transistors and our current CPUs. Because currently you have a huge power consumption. So nowadays we have 200-watt chips. Like you can bake some eggs there on the CPU because it's generating so much heat. So we are talking about a lot of power consumption. But these quantum chips should theoretically be running with much, much less power. So this is actually something which I read. Not sure whether this is correct or not. But even the computed power consumption of the shielding of the system from the environment and the computational unit itself should be smaller than with the classical computers and with the huge supercomputers nowadays. So it should be less. That's my understanding. So the other question, it would require a lot of math to work with quantum stuff. Would be some better interface for more down-to-earth programmers, or would it be only for experts? This is a good question. I'm not sure myself, because, you know, problem is, let me just show you the theory behind this. Okay, so if I go into the linear algebra and the mathematics behind quantum computing, you can see that it's scary. It's really scary. So if you are not good at maths, you are not good at working with matrices or matrices, it can be really tricky to understand this. So on the other hand, probably you would need to read through some fundamentals. So I just opened something which has 400 pages and it's just mathematics. So it's just crazy. Let's quickly go back. But again, each programming language, like the Q# programming language, is also an abstraction. So you can abstract away this mathematics behind it, as currently you are also abstracting away the mathematics behind the classical computing. So currently you are not interested in working with the logical gates and so on and so on. So there is a good level of abstraction. And in this Q# language, if I go to the API reference and the libraries, you can see that there are a lot of operations already that are implemented by the designers of the language. So I would say if you understand the concepts and you understand conceptually what kind of operations you can use, you should be able to program it and you should be able to do quantum programming. So I think if you are interested in programming and you have some basic knowledge of classical programming, you should be able to do this. I don't think that this will require some very special skills. Probably it will be a bit tricky, especially at the beginning, but once you get familiar with the language and with the algorithms, hard to say. Probably it will be not that much quantum programmers and, for instance, JavaScript or C# programmers. But I also don't think that you need superpowers. So maybe something in between. Hard to answer this question definitively. I myself am not sure at the moment. Okay, and these are all the questions we have so far. So let's get back to programming and let's go and actually do something in Visual Studio for change here. This is the same principle. So here, if I search for a template, I already have the development kit installed. So I just go create a Q# application and I create the project. And the project should be created. So okay, here you see the very basic project we had before. Let me copy this one over. And I actually found a nice trick. So if I unload and then reload the project in Visual Studio, those ugly error messages should be gone. So hopefully Microsoft fixes this. This was not broken a couple of days before, and now it is, of course. So it's not that good, but yeah, it definitely shows that they are working on it. Okay. So here we have the same program we had in Visual Studio Code. It's just a matter of taste. You can see the same program here. And this is the sample random number generator. So if I go and hit Control F5, this is the command in Visual Studio that builds and runs your program. It should give us some kind of result, hopefully a random number. So let's see if it's working. It takes some time. But we should be getting there. Yeah, so yeah, now it gave me a 10. Okay, I'm not sure whether you can see it. It's a bit small window, but now I'm getting a 19. And you know, again, I'm getting a 7. So definitely it's working. What's fun here is that debugging should also work. So now if I try to debug this program and I hit F5, I'm actually stepping into the program. And now I can see that we have this array of bits here. It's probably a small window, but I can step through the code and I can see that, first I was getting a 0, then I'm putting a 1 into the array, and then I'm getting a 1 again. And you can step through the program and you can see the variables and so on and so on. So this is also a very nice feature. And I think it should be also available in Visual Studio Code. Okay, and let's have another demo, and this will be the last one I will be showing you, and then I will show you some more advanced algorithms, and that should conclude the workshop. So I will just copy paste some stuff here now, and I also need to create a new file, and this will be a C# code. So let me name this run C#. And I already have something prepared from my cheat sheet. So I'm just copy pasting the code here. All right. All right, it should be okay. And now I will try to build this application. And until then, I will try to explain what this program is doing. So let's start with the C# part. As I was mentioning to you, at this point, we were using these entry points. And this was generating an automatic C# code which created the simulator, and then it ran the quantum program. Now we are able to do this also manually. So here you can see that what the C# code does, and it compiled, so success. You can create a quantum simulator, which will simulate our quantum computer. And what this is doing is we are declaring two initial values, a 0 and a 1. And then we are going through these values. So first we take 0, and then we take 1. And then we are saying to run our operation 1,000 times and give us back the results. Okay, and what this does is that this test bell state, this is actually this operation. Because what's happening is that automatically C# code is generated for these operations. And now I'm able to run a Q# operation from C#, which is nice. By the way, I'm not sure whether you are you have some experience with programming C# or some other languages, but you are not necessarily, you don't need to stick to C#. You can also use Python, for instance, which is also a very popular language, to run Q# code. So you can either use C# or you can use Python to actually run these Q# quantum codes, quantum programs. It's totally up to you. I'm a C# programmer, so I'm working with Microsoft for 10 years now, so I'm using C#, but you can use Python as well, for instance. But let's get back to this code. So I'm running an operation, and if I run this code, what I'm getting is that here you can see I had zeros 501 times, ones 499 times, and the agree is 1,000. And then another, I was initializing this another time, and then I was getting a number of zeros, a number of ones, and agree is again 1,000. So what does this code do, and what does this mean? So we are calling this test bell state operation, and here you can see that we are allocating 2 qubits. Okay, we are setting the first qubit to a given value, and then we are setting the second qubit to 0. Okay, so this is the trick, because initial is coming from the C# code. So the first time we are setting this to 0, this qubit to 0, and the second time we are setting this to 1. Okay, and how we are doing this? Very simple. So we have the desired state. If it's not what we are measuring, of the qubit. So let's say the qubit is in a position of 1 and we want a 0, then we apply the X operator, and the X operator is something that flips the qubit from 0 to 1. So this set operator will make sure that what we send here as an initial value, it will set the qubit to that value automatically. So we are setting the first qubit to the initial value, so the first time for 0 and the second time to 1. And we are setting the second qubit to 0. And now we are introducing another operation. You can remember that during the theory I was discussing also the quantum entanglement. So now what we are doing is we are putting the first qubit into quantum superposition via the age operation, and then we are applying the C0 operation to the first qubit and the second qubit as well. So what this will do is this will entangle, the C0 operation is actually something that will entangle the two qubits. And this is a logical operation, as currently you have NAND gates or OR gates. This is a C0 gate, and this will put these two qubits into the superposition. So then if you measure the first one, you should get the same result for the second qubit as well. So agree means that the first qubit has the exact same value as the second qubit. And then we are setting both qubits to 0 because this is a requirement for not getting errors in the system. So with the C0 operation, we are demonstrating quantum entanglement. And we are able to put these two qubits into an entangled state. And then we demonstrate it by measuring the first qubit and seeing that actually, if we measure the second one, we'll have the exact same value as the first one because they are entangled. So this is what it means that we agree 1,000 times and we are running this simulation 1,000 times. So it's working fine. And we are running a bit out of time, but this was the last example and the last demonstration I wanted to show you. So I think it looks pretty interesting. As I mentioned to you, let's get back to this page. So all you need to do, if you are interested in this quantum programming with Q#, is to have a look at this Microsoft Quantum documentation. And all the programs that we actually went through now, you will find here. So you can see the quantum random number generator and so on and so on. So that's nothing that I invented. I just took the latest state because there is some explanation for these as well. And I just showed it to you. So these are already some examples here, but there are some more sophisticated examples here as well, of course, which are more complex and more complicated. So in this tutorial section, definitely you can find some code examples, and then there are also some quantum katas, which is an open source collection of already written algorithms. So here you can find a lot of interesting algorithms written in Q#, which are very, very, very nice, probably. I haven't had a look at this, but you can do some fancy stuff here. For instance, some of them is called teleportation and so on. And there are some classical algorithms as well, which are implemented. So, for instance, there is a search algorithm, and maybe this will be the last one we can touch. Also, let me know if you have some questions. That's probably the time to type them in, because then we will not have more time. So what this algorithm means is that you have an arbitrary number of records in a database. So for instance, you have a telephone book, okay? And the book is not sorted. So you have some names and then you have some numbers, telephone numbers belonging to those names. If you would need to find a given number on a classical computer, you need to do a lot of operations. For 1 million names, you need to do in average 500,000 operations. With quantum computing, you can do around 1,000 operations and you arrive at the result. So doing research on a quantum computer would take much less time than on a classical computer. And how this is working on a high level, this is also written here, so if you are interested, you can investigate, and there's also a nice explanation. But what this will do is that this will create a superposition of all these numbers, and then it will apply a specific algorithm that will enhance the number within that superpositional state that we are looking for. So that number will be much more relevant. And this is done on a superposition of all these states. So by applying some specific algorithm, that number will be much more relevant. It will be much more measurable than the other numbers. Because there is one important thing I forgot to mention. When you measure the result of a quantum program, you don't measure it with 100% probability. So you arrive at a result, you do some measurement, and you can say that, okay, we have this measurement, and probably this is 70% that this measurement or this result is correct. So you just get a probability. And once you measure this system, you will get to the result by measuring it with a given probability. So then the number that you were searching for will be powered up and will be measured, and you can then measure this number with a given probability, and you arrive at this number. So this is a very typical example of a quantum algorithm as well. Very hard to explain it in a couple of minutes, but here it is also described, so you can have a look and you can investigate how this is working. So you have a lot of Q-sharp libraries also for different applications like chemistry, machine learning, and all these different good stuff and applications. So it's a very interesting area, I would say, and this is definitely coming. So if you would be interested in doing this quantum programming, maybe in a couple of years you would be able to also find some jobs where there will be hiring quantum programmers for Q-sharp, let's say. So let's see how it goes. As we have just 3 more minutes left, I think that we can finish the workshop. This will be probably everything from my side. And if I see it correctly, there are no other questions on Slido as well. But let me double check just to make sure. Yes, I'm not seeing any other questions. So yes, probably this is all that I wanted to show you and talk about. I'm just thinking whether there is anything that I left out, but I think that we pretty much covered everything with the time we had. So feel free to experiment with this Q-sharp language, with Visual Studio Code. I strongly recommend this text editor because you can install it pretty much everywhere. So macOS, Linux distributions, and also Windows. So it's not a problem to use this. It's really fast. It should work just fine. You just need this quantum development kit, as I said, and you can write Q-sharp programs to be prepared for Azure and Microsoft to provide actual quantum hardware. And then we will not need to run this on a simulator, but we will actually be able to run this on a cloud, quantum computer and quantum machine. So, yeah, I think that is it from my side, and I would like to thank you for your attention. I was happy to be here today with you, and hopefully you will take something away from this topic, and hope to meet you somewhere in person, if this will be possible anytime in the future. So I think this is it from my side. Have a nice rest of the day, and good luck in the future with your career as well. So thank you very much.